Welcome everyone, and welcome to the fifth of our six videos about the gas laws. We're almost done. Now in today's video, I want to talk about something called the ideal gas law. And the ideal gas law takes into account how many moles of the gas you have. Because when you think about it, if you have a container and you put more moles of the gas in that container, there's going to be more molecules there, and that gas is going to behave a little bit differently than if you have fewer moles in the container. So I'm going to start sharing my screen now, and let's go over the ideal gas law. Alrighty. Okay. So here we have the ideal gas law, and the ideal gas law is pressure times volume, PV, equals nRT. N is the number of moles, R is a constant, and T is the temperature in Kelvin. So if you look here, we've got the gas law, PV equals nRT. P is the pressure of the gas. And usually if you're looking at the pressure in the gas, you're going to see it in a couple different kinds of units. The two most common you're going to see are atmospheres or kilopascals. You might also see millimeters of mercury, which is the same thing as torrs. But these are the two most common units. And probably the most important thing to remember is what value of R, the gas constant you use, is going to depend on your units of pressure. If in the problem they give you the units of pressure in atmospheres, you're going to use this number, 0.0821. If they give you the units in kilopascals, you're going to use this number, 8.31. Now, you do not need to memorize either of these numbers, okay? You would be giving these in any problem. And the gas constant is also pretty easy to look up online. So P is pressure. Pay attention to the units. V is volume of the gas. And no matter what volume of the gas you're given, you want to convert it to liters. Why? Let's go back to R. Both values of R I have here are in liters. You always want your units to match up so that your calculation is appropriate. So if I give you milliliters, you need to turn that into liters. N is the number of moles you have of the gas, okay? T is temperature, and remember, in the gas law problems, whenever temperature occurs, you always want to change it to Kelvin. Why Kelvin? Kelvin is an absolute temperature scale, which means it has no negative numbers. You obviously can't have a negative volume of a gas or a negative number of moles. So whatever temperature we give you, you have to turn it into Kelvin. All right, so that's the ideal gas law. So let's do a couple of problems with this, shall we? Okay. So let's say, let's start off simple. And let's say I give you a gas and I tell you the pressure of the gas is 2 atmospheres. Okay. Uh, the volume of the gas is 500 milliliters. And the temperature of the gas is 21 degrees Celsius. Okay, I want to know if this is the ideal gas, following the ideal gas law, how many moles of the gas do I have? All right, so I'm going to start off with our ideal gas law, PV equals nRT. Okay, we want to figure out the number of moles of gas, so we're going to divide both sides by R times T. RT is going to cancel out on the right. So we get the number of moles of gas we have is going to be our pressure times our volume divided by the gas constant and the temperature. Now, before we plug our numbers in, let's make sure we're using the correct units. Pressure is in atmospheres in this problem. So if you go back to the last thing I was showing you, if pressure is in atmospheres, the value of R we're going to use is R is 0.0821 liter atmospheres per mole Kelvin. Okay, now volume is 500 milliliters. We need to convert that to liters. And of course, 1 liter is 1,000 mils. Whoops, 1,000. Okay, so our volume is going to be 0.5 liters. Okay, temperature, we always want to change to Kelvin. So it's going to be 21 plus 273 is 294 K. All right, now that we've worked out the units, and remember R is going to be 0.0821 liter atmospheres per mole Kelvin. Now that we have all the units figured out, let's go ahead and plug in our numbers and see what we get. Okay, so pressure is 2 ATMs, 2 atmospheres. Our volume is half a liter, 0.5 liters. This is going to be divided by R, and remember, since our pressures in atmospheres, we want to use this value of R, 0.0821 liter atmospheres per mole Kelvin. And our temperature is 294 K. And that is going to tell us how many moles we have. Now, let's go through and check our units and see which units are going to cancel out here. Well, ATMs are in the denominator and the numerator, so they're going to cancel out. Liters are in the numerator and denominator, so they're both going to cancel out. And kelvins are going to cancel out. All right, what are we left with? We're left with 1 over moles. That's the only unit we're left with, which is going to work out to moles, which is what we want our answer to be in. All right, so let's take out our calculators. All right, and we've got 2 ATMs times 0.5 divided by 0.0821 divided by 294. And we get 0.041. N is going to be 0.041 moles. And that's all there is to it. All right, let's do one more problem. Let's do one where we know the number of moles, and let's say we don't know volume this time. Okay, so let's say I tell you pressure is, let's go with 1.5 ATMs. Okay, temperature, volume we don't know. Number of moles, let's say we have, I don't know, 3 moles of the gas. And our temperature this time is going to be, let's go a little crazy and have it at 110 degrees Celsius. All righty. Now, again, we're using ATMs and pressure. So the R value we're going to use is 0.0821 liter atmospheres per mole Kelvin. All right, and this time we're looking for volume. So the algebra is going to be a little bit different. PV equals nRT. We want to find volume, so we're going to divide both sides by pressure. All right, this time pressure is going to cancel out. Okay, so let's check our units. As I said before, pressure's in ATMs, so we're going to use this value for R, 0.0821 liter atmospheres per mole Kelvin. Okay, temperature is 110 degrees Celsius. We need to convert that to Kelvin by adding 273. So that's going to be 383 Kelvin. All righty, and we're ready to do this problem. So volume is going to be N, which is the number of moles, which is 3.0 moles, times R, which is going to be 0.0821 liter atmospheres per mole Kelvin, times our temperature, which is 383 K. Kind of squeeze this in here. And all of that is going to be divided by our pressure. And our pressure is 1.5 atmospheres. All right, let's cancel out our units. Moles are going to cancel out with moles. Kelvin, sorry if that's a little hard to see there, is going to cancel out with Kelvin and leave us with 383. Okay, and ATMs are going to cancel out with ATMs. So the only unit we have left is liters. So to do this calculation, we're going to do 3 times 0.0821 times 383 divided by 1.5, and we get that the volume is 62.9, which if we're watching our sig figs, we have to round that to 2 sig figs. So our volume in this problem is going to be 63 liters. All right. Now, if we go back and look at this, let's see if that kind of makes sense. We have 3 moles of a gas. Now remember, at standard temperature and pressure, which is room temperature, which is it's 0 degrees Celsius, and 1 ATM, 1 mole of gas that takes up 22 liters. So if we had 3 moles, we'd expect somewhere around 66 liters, but in this problem, we've got it under increased pressure, so that's going to squeeze the gas down a little bit and take our number below 66. Okay, probably take it down probably about 50% or so. But we're also heating up the gas to boiling, past boiling, and that's going to make it expand again. So we would expect something in the ballpark of around 60 something, somewhere around that, and we do. So that answer kind of makes sense. Alrighty, hope that makes sense, you guys. Have a great day.